Today we are going to discuss about Lagrange theorem. This is the most important theorem of the abstract algebra. This is the first milestone of abstract algebra. This theorem says order of subgroup divide order of group if group is finite. Moreover, the number of distinct left cosets of H in G is order of G by H. Similarly, the number of distinct right cosets of H in G is order of G by order of H. Now its proof. Let G be a finite group. This theorem is given for the finite group. So, and H be a subgroup of G, and let A1H, A2H and so on ARH are the distinct left coset of H in G. You can define right coset. If you define right coset, you must define every coset are right coset. Here we are defining left coset. So, and they are left coset which is distinct for each A belongs to G, G be a group. Here we have AH equals to AIH for some I, because AI here AI, that is AI means A1 maybe A2 A3 and so on AR. A कोई मैं G का एलिमेंट ले रहा हूँ, तो अगर मैं AH कोसेट बनाना चाह रहा हूँ तो ये किसी न किसी AI ये इस कोसेट के इक्वल होगा, बिकॉज दे आर ऑल पॉसिबल but distinct left coset of H in G. A belongs to always AH by property 1. Last property we have proved, property for cosets. Thus, for all A belongs to G, it implies A belongs to AI H for some I, because here AH equals to AIH. So we can write this, that is G can be written as A1H union A2H union and so on U ARH. 1H A2H and so on ARH are distinct left coset which is given here. We already assume this. AIS all are distinct left cosets. Thus we know every coset are either disjoint or identical, but there are all coset are distinct, so they are disjoint. We can write phi for all I not equals to J. Thus we can write order of G can be A1H plus order of A2H plus and so on plus cardinality of ARH. AIH AJH. We can write this equals to H, so we can write this is H plus H and so on plus h. There are r copies, so we can write r into h. This is order of g. We can say order of h divides order of g, where r is number of left cosets of h in g. Thus r equals to, this is order of g by order of h. Note first, converse of Lagrange theorem not true. That is, if n divide order of g, then we cannot say there exists subgroup of g whose order is n. We cannot claim that there exists h subgroup of g such that equals to n. Okay. For example, A4 doesn't have subgroup of order 6. This is alternating group, we will discuss later. This is counter example, please keep in mind. This is most important example for converse of Lagrange theorem not true. Number second, number of left cosets of h in g can be written as this symbol. This is nothing but order of g divided by order of h, any order of g by order of h. Now some corollary of this theorem. All are most important corollary. First corollary, order of element divides order of group. This is small proof. If g be a finite and a belongs to g, where g is finite, then we know the set generated by a can be written as this. We also know this is the subgroup of g, and order of this subgroup is nothing but order of element a, but Lagrange theorem says order of subgroup divide order of group. Thus order of a should divide order of group. इनके एप्लीकेशन भी हम सीखेंगे, बहुत ज़्यादा इम्पोर्टेंट है ये हमारा ये लैग्रांज थ्योरम। इसके अगर एप्लीकेशन के बारे में आप सीखेंगे तो बहुत इंटरेस्टिंग है ये। अब देखिए, जैसे यहाँ पे मैं कह रहा हूँ, फॉर एग्जांपल एक एग्जांपल ले लेते हैं। मैं कह रहा हूँ ग्रुप का ऑर्डर है 100, एक सब ग्रुप है सपोज एच जिसका ऑर्डर है 30। क्या ये एच जो है इसका सब ग्रुप हो सकता है? तो लैग्रांज थ्योरम सेज ऑर्डर ऑफ सब ग्रुप डिवाइड ऑर्डर ऑफ ग्रुप, बट 30 कैन नॉट डिवाइड 100, it implies H cannot be subgroup of G. तो अगर ऑर्डर गिवन है ग्रुप का और सब ग्रुप का तो हम क्लेम कर सकते हैं ये उसका सब ग्रुप नहीं होगा। ये कैसे हम लिख रहे हैं, अब देखिए एप्लीकेशन ये कैसे हमने लिखा। Lagrange theorem says order of S यानी ऑर्डर ऑफ सब ग्रुप डिवाइड ऑर्डर ऑफ ग्रुप। इसका मतलब ये है अगर S be a सब ग्रुप ऑफ G, here G is finite, okay, then order of S should divide order of group. This is P statement, this is say Q statement. If negation of Q imply negation of P, that means if P imply Q is true, then not Q imply not P is true. It implies that if order of S doesn't divide order of this group, it implies S cannot be subgroup of G. Okay, तो 30 जो होगा, 30 नंबर जो होगा 100 को डिवाइड नहीं कर रहा है, तो ऑर्डर 30 का G के पास कोई भी सब ग्रुप नहीं हो सकता। ठीक है, S कैन नॉट बी सब ग्रुप ऑफ G। इस टाइप से हम डायरेक्ट बता सकते हैं। अब सिमिलरली ऑर्डर ऑफ एलिमेंट के लिए अब देखिए, अब मैं कह रहा हूँ एग्जाम्पल, अब कॉरोलरी 1 के लिए एग्जाम्पल है, हाउ मेनी एलिमेंट्स ऑफ order 30 in Z100. How many elements? We know number of elements of order n in Zn equals to D in Zn equals to 5D. ओके, ये फार्मूला तो होता है। अब लेकिन सबसे पहले हमें क्या करना है, चेक करना है 30 इसको डिवाइड करता है या नहीं करता है, यानी ऑर्डर ऑफ एलिमेंट शुड डिवाइड ऑर्डर ऑफ ग्रुप। ठीक, यानी ऑर्डर ऑफ ए शुड डिवाइड एन, या ऑर्डर ऑफ ए क्या है, 30 शुड डिवाइड 100 but it doesn't divide 100. Thus there is no element of order 30. 2 बहुत important, बहुत useful. If order of group equals to P, where P is prime, it implies G is cyclic. अब इस कोरोलरी से हम बता सकते हैं प्राइम ऑर्डर का जो भी ग्रुप होगा वो हमेशा साइक्लिक होगा, हेंस अबेलियन स्टेटमेंट ग्रुप ऑफ प्राइम ऑर्डर इज साइक्लिक। इट्स प्रूफ, लेट ऑर्डर ऑफ G इक्वल्स टू P prime, where P is prime. Okay, we have to show G is cyclic and A belongs to G such that A not equals to identity. Then we know a set cardinality of set generated by A should divide order of G by first corollary. Since order of A should divide order of G, but A not equal to identity, thus Thus order of this subgroup equals to must be P. This is the order of G. Therefore G is cyclic. A to the power order of group equals to identity. Let G be a group, rather finite group, and let A belongs to G. It implies A to the power order of G must be E. By Corollary 1, order of element should divide order of group. It means that there exists some integer k belongs to such that order of A into k equals to order of G. Thus A to the power order of G equals to A to the power order of A into k, that is order of A to the power order of A to the power k. It is always equals to E to the power k equals to E. Now corollary fourth. This is Fermat's little theorem. This theorem says for every integer A and prime P, A raised to P minus 1 equals to 1 modulo P. This is the Fermat little theorem. We are going to be proved by Lagrange theorem, but here integer A and prime P are given. So by the division algorithm, A equals to Pm plus R with less than P. We can apply we apply division algorithm for P and A. Now we to show A raised to P minus 1 equals to 1 modulo P. Okay. For this we are sufficient to show R raised to P equals to R mod P. If R equals to 0, then we are done, because the 0 equals to 0 mod 0 to the power P equals to 0 mod P. This is whole. So if R is not equal to 0, that is, इसका मतलब क्या है, 0 this. For this R, we assume R belongs to U P. This is the set 1, 2, 3, P minus 1. This is co-prime with P. By the corollary third, because R belongs to this, so R to the power order of UP must equal to identity, that is 1 R. This is order of, this is P minus 1, so this is 1, so R to the power P equals to R. Thus we are done. So corollary is, so we can write R to the power P equals to R mod P for any P. If we choose R between 0 to P, we can say A to the power P R mod P, sorry, A or A to the power P minus 1 mod P. This is question based on the Lagrange theorem. Group order है 60. Then what is the possible order of the subgroup? By Lagrange, order of subgroup divide order of group. We have to find divisor of 60, that is possible order of S equals to 1, 2, 3, 4, 5, 6, 10, 12, 15, 16.